Hi, my name is Carson Honkala, and I'm an undergraduate research assistant here at Michigan State University. And today, I'll be going into our findings on Pion and Kaon distribution amplitudes in the continuum limit. First, I'll give a brief overview of the process behind our research in its entirety, and then dive more specifically into the parts of the research I was involved in. Since I'm an undergraduate computer science student, I won't be going into too much detail on the Lattice-QCD aspects of our research. So, if you're interested in these or have questions regarding it, I'd advise you to check out our article on ArcSIF, which is linked at the bottom of the screen here. As the title of the research suggests, we're doing a Lattice-QCD calculation of Meson distribution amplitudes. A meson is a subatomic particle made up of a quark and an antiquark. In our case, the mesons being used are pion, kaon, and eta s. A Meson distribution amplitude is a way of plotting the fraction of momentum that a meson contributes to a particle versus the probability of that fraction of momentum occurring. These Meson distribution amplitudes are important since they can be used in a variety of related physics problems, such as the decay of B mesons. The lattice data used is generated using supercomputer simulations, and then through a series of calculations, you can calculate the lattice matrix elements, which are then used to extract the x-dependence of Meson distribution amplitudes with two main methods. One, you can fit to an assumed distribution form with a one-loop matching kernel, or you can use a machine learning algorithm trained on pseudo Lattice-QCD data. Since I was involved in the machine learning algorithm method of extracting the x-dependence, that is what I will be covering for the rest of this presentation. The machine learning procedure is fairly straightforward and can be broken down into three steps: generating the pseudodata, developing the model, and testing the model. Machine learning involves using a dataset of known inputs and outputs in order to create a predictive model that can predict an output from a given input. The issue with this is that while we have our input data, which is the Meson lattice matrix elements that we calculated earlier in the study, we don't know the exact distribution amplitudes of these mesons. Luckily, certain constraints are known about them, namely that at x equals 0 and x equals 1, the function must equal 0, and that the area under the curve must always be 1. If you have knowledge of probability density functions, this should seem familiar. Since this is the first attempt to extract distribution amplitudes from real lattice matrix elements, we use a common distribution amplitude fitting form. This form is plotted on the right in order to graphically show that these constraints are being met. Using this function form, we can create fake or pseudo data. With corresponding pseudo input data, we can create 100,000 samples, each of which have random variance applied. This represents observed samples if the data were actually real. Now that we have a set of data in which we can train a machine learning algorithm, we use an MLP regression, which is a neural network machine learning algorithm built into scikit-learn. Scikit-learn is a Python package that has a variety of built-in machine learning functions. The MLP regression has many parameters that can be tweaked, and in order to optimize this model, we can use GridSearch-CV. GridSearch-CV takes multiple inputs for each possible parameter that can be tweaked, and outputs the MLP regression that predicts a set of test data most accurately. Now that we have an optimized machine learning model, we must prove the model's ability to extrapolate. We must do this because while the functional form used to train the model was similar to that of real matrix elements, it is not exactly the same. Therefore, in order to prove that our predictions of the Meson distribution amplitudes are accurate, we must show that the model can accurately extrapolate. We can do this by using a simple sine function. This function shares the same constraints as the distribution amplitude, but does not follow the exact same functional form. The black line on these plots represents the actual value of the sine function, while the blue band represents the model's predicted value of the sine function, plus uncertainty. As you can see, the prediction very accurately follows the actual value of the function for each of the different powers the function was raised to. This is very promising evidence for the model's ability to extrapolate. With the model's ability to extrapolate to functional forms it wasn't trained on proven, we can move on to predicting actual Meson distribution amplitudes from the real lattice data. Pictured here are the plots of Kaon, Pion, and eta s in order. As you can see, the results are very similar to that of the fit method of extracting the distribution amplitude for Kaon and eta s, which makes sense, since the fitting form is the same. The prediction for Pion is significantly noisier and deviates from the fit results more significantly, however. This can most likely be explained by the fact that the lattice data for Pion is far more noisy than the other two, and may suggest that the machine learning model struggles with high variance input data. Regardless, for a first attempt at calculating the distribution amplitude using machine learning, these are very promising results. Overall, more tuning is required to improve the stability of the prediction. A more stable result can be achieved with more precise data. So, future studies with higher precision data should allow a trial of more function forms and remove the dependence on the current one used. And hopefully, these will improve the accuracy of our final prediction model. However, all in all, this is a very promising first result.